Okay, now let us move on to the Iir filters. Iir filters. So once again, let us consider a transfer function h of z is equal to b naught z cube plus b1 z squared b2 z plus b3 divided by z raised to the power of 3. So once again, following the previous procedure, we can determine the difference equation. So the difference equation is given by y of n is equal to b naught x of n plus b1 x of n minus 1 b2 x of n minus 2 plus b3 x of n minus 3. And if that is the case, we can be generalizing this form. Y of n can be written as summation bk x of n minus k, where k goes from 0 to capital N. Note that there is no second summation for y of n minus k. And similarly, h of z can be written as summation bk z raised to the power of negative of k, k which goes from 0 to capital M. Otherwise, if we factorize this polynomial, we can write h of z to be equal to b naught capital pi, that is running multiplication where k goes from 1 to capital M, 1 minus ck z inverse 1. Hence, once again, we'll look into the difference equation. And in this case, in the difference equation, the current output y of n is only dependent on the present input along with the past values of the input, and whatsoever not on the past value of the outputs. This is the most defining feature of the Iir filter over the Iir filter. So, say for instance, once the filter is, once the input of the filter, say this being our filter having a transfer function h of z, the input being x of n, the output being y of n. Say we are giving input and consequently getting outputs. So now if the input is switched off for a sufficient amount of time, then what will happen to the output? The output will eventually start to decay. That means, say if x of n is switched off at the instance n, then y of n will only give samples output for the next 3 samples only. And after the third sample, this x of n will become the value of x of n minus 3, and this will decay to the point of 0. That means, in the Iir filter, if the input is switched off, after a sufficient amount of time, the output will reach 0. Hence, there is no case of recursion in the Iir filter. So, in this case, if an unit impulse is provided in the input side of the filter at n equal to 0, then after a certain time, say this is at n equal to 0, we give an impulse. So at n equal to 3, that is at n of 3, y of n will become 0 for this transfer function. because this sample will shift back to the n minus 3 position, and for the n minus 4th position the value will become 0. Now, points to be noted. Looking at the transfer function, it is quite obvious that the value of the pole that is in the denominator will always occur at the origin. Let me simplify this. Say dividing the numerator and denominator by z raised to the power of 3, this becomes b0 plus b1 z inverse plus b2 z inverse 2 b3 z inverse 3. So the pole may occur. So there are numerous poles which may occur at this point, but all of them must be in the origin of the unit circle. All the poles will be in the origin. A more constructive way to define that is if we factorize the polynomials over here, the numerator will have factors and the denominator will have factors z minus 0, z minus 0 and z minus 0. So if we multiply these three values, we'll get z cubed. So z minus 0 is nothing but a pole on the origin. So this is a defining feature of the Iir filter, that 0 may occur at any position on the z-plane, but the poles must always occur at the origins. So now let us look at the block diagram of an Iir filter. So the block diagram of Iir filter, if we get x of n as an input and delay z inverse 1 in the z domains, essentially means delaying the signal in the time domain. At this point the signal will be x of n minus 1, and again delaying it, it will result in x of n minus 2, and so on. So for the nth number of delay, this will be z minus 1. For n different delays, the output here will be x of n minus mth number of delay. So what an Iir filter does is that it takes all these values from this point and over here, multiplied by a weight. That's why it is a weighted input rather than a pure input. This is b1, b2 and similarly bm, and simply sums it up. So we use an arithmetic adder. This will be our output y of n. This is our block diagram representation of an Iir filter. Now what will be the case in the Iir filter? Let us look at that. Okay. So in case of the Iir filter, let me write down the difference equation. Summation bk x of n minus k minus summation of ak y of n minus k. Here k goes from 0 to capital M, and here k goes from 1 to capital capital N. Okay, so we get an input x of n and make it delay, z inverse 1 being the delay by one sample, z inverse 1. So here the signal will be delayed by two samples. So at this point the value will be x of n minus 1. and it will be x of n minus 2, and so on. So for the mth delay, z inverse 1, capital mth delay at this point, the signal will be x of n minus m. So what we need to do is just sum up these values, x of n minus 1, n minus 2, sorry, x of n minus 1, n minus 2, n minus m, and provide it with some weights. So let's give some weight. Here it is b naught for x of n, it is b1, this will be b2, and consequently this will be b capital M. And the result will be nothing but a summation or an arithmetic adder. Okay, now we have solved for this summation. So for the next summation, if this is the output y of n, the output is delayed by z inverse 1, again it is delayed by z inverse 1. So here the output will be y of n minus 1, be y of n minus 2, and so on. So it will go until y of n minus capital M. So what it will do is just sum up these values of the previous outputs with some weight a of k. So here the weight will be a1, here will be a2, at this point the weight will be an. Now since the direction of the weights and in the reverse direction to that over here, there will be a negative sign, and this negative sign is corresponding to this negative sign over here. So simply add this up using a linear addition operator. So this will go over here, this will go over here, and this is the output side and this summation. So all we need to do is just connect this to summation operator, and we get the block diagram of an Iir filter. Now points to be noted: as I have shown the recursive action of Iir filter, see here, sorry, this arrow will not be here, this will be going in this direction. If this is our output, then the output will always depend on some previous value of the current output. That's why there is a loop forming over here and over here and over here. That's why the Iir filter is known as a recursive filter. So these are our basic characteristics of the FIR and the Iir filters. Now let us move on to some specific properties of FIR and Iir filters.